All right. Hello, everyone. I'm Daniel from Runtime Verification. I'll let Robert introduce himself. Oh, now?
Okay, yeah, I'm Robert from OtterSec.
I'll be doing the first half of this talk. So we're going into the common security pitfalls, how to avoid them. One thing that I noticed during Muli's talk was a lot of people put their hands up to know about formal verification. I definitely aimed for an audience that wasn't as familiar with formal verification, but maybe we'll have fun along the way anyway. We both do a lot of smart contract audits for Stellar and other ecosystems, and we were deciding what to do for this talk, and probably the most common thing that we see is, or at least in my experience, is just simple logic errors. They get caught that we have a pretty good avenue that we could have got around. So in this talk, I'll just quickly talk about what I mean by a logic error. I'll talk about an example from an audit where we found one, and then some practical ways, without having a PhD indeed, for how to get through these for the typical developer. So, as I said, logic errors are very common. And they're very hurtful to your ego as well. And they can be quite difficult to detect. Often this is involving some sort of tricky edge case that you just didn't think, and so what you're reasoning about is far too simple. But there's also, sometimes they're easy to solve, and you've just got to handle that case that you missed. But sometimes they can uncover that there's actually a fundamental flaw in your design, and you have to go quite a few steps back, which is never fun. So we audited FXDAO, and it was fantastic. We had a great time auditing it. There was one bug that we found that is a little bit fun, so worthy of having for this talk. But a quick description of what FXDAO is: they do over-collateralized positions for stablecoins. Two that I'll use in the example is one for Great British Pound, one for USD. And these debt positions are held inside a data structure called vaults, which is a linked list, and it's sorted. You want to know that the debt positions that have the worst leverage are closer to the head of the list because they're the ones that might be at higher risk of liquidation. And it's important that when you create a new position into this vault, it goes into the right spot. And so vault create new position does maintain the ordering. Or does it? If it did, it wouldn't be a very exciting talk. But here's a diagram that I made to represent it. So this is a linked list of vaults, and at the top there's how much leverage. The top row is for Great British Pounds, the bottom one is for USD. You can see that the leverage is ascending, so 124 is less than 137, 183, much the same down the bottom here. If you wanted to add a new vault in, so we've got Great British Pounds here, the leverage is 159%. The only correct position for it to go is right there. That's the only correct answer. So there's a bug in this code, of course. And so what cases got missed? What was the edge case that went wrong? That position is meant to reject. It colors red. It's correct that it was meant to reject, and that case got caught. Indeed, you could not put a vault there. Perhaps you could put a vault here earlier, getting the ordering wrong this way. That was thought of as well. But the head of the list is a different special case on its own. But actually, that one got thought of as well. And in fact, it is impossible to break the ordering. This is the only correct outcome, is that you don't get the ordering wrong. So you have sort of been tricked. But everyone will see the list down the bottom and probably know that what I'm getting at is it possible to put the Great British Pounds vault into here? It shouldn't work because it's the wrong currency, but in fact it will work because all it checks is the ordering maintained. And in terms of the list, the one beforehand and the one after it is indeed a correct order. And so I can only imagine that this would have been quite a pain had it have gone to production and one day a list of one currency was mixed up with the other currency and wondering, how did that happen? But I think this is an easy situation to get into where you are so focused on one problem, making sure that the things are ordered, that you have a whole bunch of assumptions that are obviously they should hold. Like, of course, we shouldn't be mixing up currencies, but unless you explicitly put that in the code, that's not going to happen. And so sometimes worrying about a bigger problem, you forget about a lot of smaller problems. And so we found this error, and we could have come across the same problem. We're looking at the code. We're really worried about making sure that this ordering is maintained. But we did find the bug. We didn't use a fuzzer, and we didn't use a theorem prover. All we did was we wrote out invariants, and we wrote out specifications. And looking through the code with that was sufficient to realize. And this can be done in development as well. This isn't something that needs to be exclusive to an audit by any means. And just in case people in the audience hadn't heard of these words before, invariant in the dictionary is something constant and unchanging. In terms of code, this would be a property that must exist for the lifetime of a data structure or the lifetime of the system, and the specification being if you have functions or methods, things that must be true in order to call that function, and the guarantees that it gives after you've called it, respective to the state. And so in developing this linked list, something that I would recommend, which is what we did at the audit, would be write out everything that should be true of the different components and different data structures. And if you have them written down, you're unlikely to not address them because you have your list there. And I think that's an important step that actually gets missed, is having everything down in a way that you can check off, like, do these actually get adhered to? So one, obviously this is going to be massively simplified. There was a lot more that happened in that for the actual protocol, but two things that would have been, an example to have down is that the vaults must be sorted on vaults.leverage, and every vault must have the same currency. But writing these down, it would be the first step. You'd want to go beyond that, and you'd want to add them to some sort of a specification. So in Rust, we're able to have doc strings that when you put your mouse over, if you got the Rust analyzer installed, you can hover over a function, and it will show you the doc comment up the top. And so these invariants, you can think about, okay, well, how does create new position mutate the state? What's it doing? What's my code trying to do? And what things does it need? It needs to take in a sorted linked list. It promises it's going to give back a sorted linked list. And it promises that all the currencies in there are going to be the same. And so these comments here aren't compiler directives. They're just essentially note-taking to yourself to make sure, does this work? And as you continue development and you're going to use create new position in some context, you can make sure that if all your invariants are addressed in all of your comments here, you can hopefully go through and you'll be able to write in things like debug assert statements. I think these are really useful because these aren't going to end up in your production code. They're going to be really useful for in development when you've written something and it violates one of these properties and you've got to catch it because it won't go through. So here, this is before the code, it's asserting the precondition, and after the code, it's asserting the postcondition. So once you've done that, of course, the step to getting the most juice out of that for the squeeze would be to try to have a test for every invariant. Try to break them. And so I think that using property tests for this, so the talk that Lee gave yesterday, he mentioned using cargo fuzz to do invariant testing. I like prop tests, but it's much the same. But being able to test or try to break an invariant, actually scrutinize it over many cases, I think that's a good way to go. And these things are things that are accessible to every developer. I think that they could be done pretty simple in terms of the development lifecycle. That's all for my one. I think on to Robert.
Sweet. You're going to hold this. No questions so far.
Okay.
There's like a live question tracker on there. Yeah, so for my half, I want to talk about storage bugs. Actually, before I get started, a big thanks to Andreas for helping write most of these slides. He's in the back over there. He does a lot of our audits. Yeah. Broadly speaking, whenever we look at a new ecosystem, like Stellar, for example, or a new runtime environment, we like to think about what are the sorts of things that are unique, right? Because the things that are unique are the most likely things to break. And I know Tomer wants to say that Stellar is really, really good and really secure. But I think, to be fair, one thing that's unique about Stellar is its storage model. And this is something that if you're a new developer on Stellar, you should really understand what's actually happening, right? For example, there's 3 types of storage, which is something that you don't really see on other blockchains. When do you use instance storage? When do you use persistent storage? And more importantly, what are the actual implications of using each of these 3? I think when we look at new blockchains, these are the questions that we're asking ourselves. And if you want to write secure code, you should also ask yourself those same questions. Like, why do they have 3 different types? This presentation will talk about that a little bit and hopefully give you some intuition for when you should use them, as well as different foot guns. First off, storage is a key value pair. So for all of these 3 types, you have a key, you have a key, and then you store some value. All contract data also has a time to live, which is, again, unique to Sorbonne. When the TTL reaches 0, the state either gets archived or deleted. And importantly, if you're a contract interacting with the storage, you have to think about what happens when that TTL reaches 0. Otherwise, it's really easy to write a bug where you think that storage exists or is live, but it doesn't actually exist, and you'll error when you try to access it. So the first one, and probably the simplest one, is instance storage. It's limited by the entry ledger size, which means that it has a max of 64 kilobytes. It's archived when TTL reaches 0, and it's used for, or it's meant to be used for, variables that are commonly accessed. So for example, like the admin key pair, or the admin pub key. Then you have temporary storage, and this is where it gets interesting. Unlike instance storage, you have arbitrary keys. But the most important part is that when the TTL reaches 0, the data gets permanently deleted. And if you're a new developer, you can already think about all the things that can go wrong here. If your TTL reaches 0 and your contract relies on that state, and it gets deleted, you might have a bug. And we'll talk through some examples of how this might be a problem. Persistent is similar to temporary, except for instead of getting deleted, the state gets archived. And you can extend that TTL whenever you want. Same with temporary and same with instance storage. Each entry is limited to the ledger entry size. So one question you might ask is, what is the implication of this ledger size limit? One common use case is we want to store a vector. And vector sizes are often unbounded. For example, maybe you have a vector of users, right? And you want to have, hopefully, a lot of users on your protocol. So the naive way you might want to do this is you have, put it in instance storage or wherever you put it, and then you just store the entire vector in that. If you paid attention, you would correctly note that instance storage is bounded, which means that this is actually a security issue, in the sense that if somebody was able to store a bunch of users or create a bunch of accounts, they could prevent future users from being created. What if we try persistent? It's also bounded, and this is a problem that, or not a problem, but this is an issue that affects you regardless of what storage type you use. So the correct solution, or a possible solution that we've seen our clients use, is you store the length, and then you store each individual entry. And the important implication here, and the important part to realize, is when you're storing stuff, you have to make sure that data is bounded. There is a hard limit on the amount of data you can store, and if you don't bound the data, then your functions can abort. Here's a real-life example where instead of storing users, as I used in my previous example, they store this is a factory contract, and they store the pools, the deployed contracts. So if you just have a vector of pools and you push to that vector, you'll exceed the instance size limit, and then it will abort. I think this is okay. So this is another bug class, and this relates to the TTL on temporary storage. So in this example, I don't know if it's possible to read here, but we have a claimable balance that we set to a claimant, and then we have a claim date, and then we use temporary storage to store this claimable balance struct. The issue that you might come across is that because this is temporary storage, it can be deleted. And when you try to claim it, it might disappear. An important implication of this is because we're on the blockchain, you can't really guarantee that people will extend the TTL. And one invariant that you should try to use is that when you lose access, it shouldn't be the end of the world. If you need the data to stay around for a long time, you should consider using either a super long TTL or persistent storage. An important caveat here is anyone can extend the entry of a TTL or extend the TTL of an entry. So you also shouldn't rely on the fact that a key expires to do something. So for example, if you have if this is some nonce that represents that some reward has been claimed, someone else could extend it and potentially deny you from claiming it again. Yeah, I think this is a similar example. One other issue, or one other big difference between temporary storage and persistent storage is that temporary storage will abort if you try to extend the TTL to too, or if you extend the TTL for too much. In contrast, persistent or instant storage does not. And the reason for this is, and this is pulled from the Sorbonne host code of actually doing the TTL extension, because temporary storage gets deleted, the way the API is coded is it wants to guarantee that you'll at least get that amount of TTL extension. In other words, for example, if you think, or the contract thinks the key will stay around for 7 months, it should actually stay around for 7 months. Otherwise, the way this API is designed, it will abort. So if you try to extend it for too long, it will actually throw an error, which is a relatively subtle difference between temporary storage and persistent and instant storage. So this is a fun bug with this example. Someone has temporary storage, and they try to extend it for epoch times config times dot epoch length. Actually, we think this is potentially some old code where they extend it to the actual end date. But in this case, because they extend it too far, or they try to extend it too far, this function will abort. And this function will actually never succeed at runtime. OK, one final bug class I want to talk about is storage updates and caching. And this is a broad issue that doesn't just affect Stellar. I think it broadly affects any sort of runtime environment where you have a key value storage system. Some other ones like Near, for example. So in this case, the general problem is you read some data out of the storage. In this case, the user balance struct. Then you do some sort of modification to it. In this case, you call charge v, and it updates storage value directly. And then finally, you write the value back into storage. So you see the red box. It sets the balance directly. Sorry, it sets the balance directly here. And the important part is because this user balance struct is cached, it will overwrite the previous value. And generally speaking, this is an anti-pattern where you have some sort of long-lasting. I mean, in essence, you're taking a reference to the value in storage. You copied it out, so you don't take a reference necessarily, but it's conceptually similar to taking a reference. You're doing some sort of modification to it, and if you modify that value in between, you might break some invariant or cause some sort of logic bug. And in this case, it's not super impactful because you only waived the fee, but maybe in some other case, it could be a lot worse. And I think I have example here, right? So for example, what if from and to are the same address? This is a relatively simple transfer function. We want to transfer tokens from one person to another. But you'll notice that the from balance and the to balance are cached. And if we transfer tokens to ourselves, we'll actually get double the tokens. I think this is a pretty informative and pretty good example of how this cache behavior can be relatively subtle. And if you don't think carefully about what you're actually writing back to storage, you can easily shoot yourself in the foot. So yeah, 3 broad takeaways. Be mindful of storage size limits. Be careful what you put in temporary storage. And yeah, one other edge case that anyone can extend the contract data TTL.